You will remember that if a molecule is formed, that as those atoms approach one another, get closer together, the potential energy of the particles decreases. And so what is happening is that energy is being released because the particles have got less energy. So where does that energy go? It goes out into the atmosphere. So bond energy is the amount of energy required to break a bond. When I make a bond, I release energy. When I break a bond, I have to put energy in order to push those atoms apart again. It follows that the same amount of energy is needed to form the bond. Now, in order to get the bond to form, I need to add energy, and that energy that I first add is called the activation energy. What does activation mean? To activate something is to get it to get started. So it's the energy required to start the reaction by making the activated complex. What is this thing called an activated complex? Let's say I get A plus B forms C plus D. Something happens in this middle space over here where A, B, C, and D all coexist as some sort of a mushmash. That is the activated complex. And we'll talk a little bit more about it in a second. Delta H is the heat of the reaction. And this delta H, that triangle there is a delta. It's a Greek letter meaning change in, is the heat of the reaction. In other words, it's the energy of the products minus the energy of the reactant. So I take all the energy of C and D, I subtract all the energy of A and B, and I get the delta H value. You'll see it a bit clearer in a graph in a second. Exothermic reactions give off energy, they get hot, and their delta H value is negative, whilst endothermic reactions absorb energy, they get cold, and the delta H value is positive. Let's look at that as a graph. Here's an exothermic graph. So we're looking at an exothermic reaction. I start with reactants, A and BC. The transition state, another name for the transition state, is the activated complex. Just the same word a different word for the same thing. And at the end of it, I have got products. Reaction starts with reactants, ends with products. The energy of the reactants is greater than the energy of the products. What does that mean? That means that I have got rid of some energy. Energy has come out. And that energy out means it's an exothermic reaction. If I took the energy of the products, let's say it was at 20, and the energy of the reactants was, let's say, at 40, I would say 20 minus 40 gives me minus 20 kilojoules. So when I have got an exothermic reaction, the delta H value is going to be negative. Here's my course of the reaction, and it is the reactants are here, and the products are up there. So let's just for a second say the reactants have got a value of 20. The products, let's say, have got a value of 60. The energy of the products minus the energy of the reactants gives me positive 40. So the delta H value is a positive number when I have an endothermic reaction. What do I mean by an endothermic reaction? It means overall I have taken energy into the reaction. The products have more energy than the reactants. The activation energy is what I need to start the reaction to get to the activated complex. I need to get over this energy hump. Now, we can look at the actual bond energy, how much energy is required to make a bond, or how much energy is released when we break a bond. You will never have to learn these values. These values will be given to you in an exam, and you are expected to just use them. What you can notice, though, is that single bonds have less bond energy than, say, double bonds, and the strongest bond energy or the greatest bond energy is making and breaking triple bonds. Bond length is the distance between two nuclei. So if I were to take two atoms like that, the distance between their middles is called the bond length. We use X-ray diffraction. In other words, we send X-rays through a substance, and the pattern that comes out the other side tells us how long the bond lengths are. Generally speaking, molecules with shorter bond lengths have got higher bond energies because these atoms are close together and they love each other and they're sharing electrons. They're very difficult to separate apart. Multiple bonds, in other words, double and triple bonds, are always shorter than single bonds because they cling in tightly with all of those shared electrons. Here's a table of the bond lengths. Again, you don't have to learn them, and you notice that single bonds are longer than double bonds, which are longer than triple bonds. The best comparison is C single, C double, C triple, where you can see that the bond length keeps getting shorter and shorter. So, if I take a look at comparing bond lengths and bond energies, if I have got a big atom, then the bond length is going to be big. Big atoms also, it's much easier to separate them because let's just take a look at chlorine and iodine. Chlorine's small, iodine is big. So if I want to separate these guys, their outer electrons are not very close to the nucleus. They're not tightly stuck in there. So this is easy to break and therefore requires less energy than this, which is hard to break. So the smaller molecules are going to have much stronger bond energies or greater bond energies. Multiple bonds will have greater bond energy and they will have shorter bond lengths. Generally speaking, if the bond length is short, the bond energy is high. That is a generalization that you can make. Obviously, if there's a big difference in electronegativity, you are going to easily be able to separate them. So if I take something like hydrogen fluoride, it will be easier to separate than something that has a non-polar covalent bond. Why? Because non-polar covalent bonds have lots of overlap. So they love each other very, very much, and it's difficult to separate them. And they're going to cling to each other very closely because they're sharing their electrons so much. So we now need to be able to calculate bond energies. They're going to always give you an equation. You might have to balance the equation, but usually you'll be given a balanced equation, and you are then expected to work out what is the net energy absorbed or released. So you're going to work out the energy of the bonds in the reactants, the energy of the bonds in the products, and then determine what is happening overall. So our first one, I've got a hydrogen molecule and an oxygen molecule in the reactants. I have got a water molecule in the products. My hydrogen molecule, there are two of them. First, let's just look at what does it take to break that bond. I look on my table, it's 435. What does it take to break the oxygen double bond? It's 500. But I don't have one hydrogen, I've got two hydrogens. So I double the 435, add the 500, and that's the total amount of energy that I need to add in order to break all of these bonds. And then I get my activated complex H, O, all in a mushmash. Oh, there's some extra H's around and about. All in a mushmash before they release energy and become water. To make water, I need to make an OH bond and an OH bond. They are 460 each. That's on the table. So in total, to make one water is 920. But I haven't got one water. I've got two waters. So I double that up, and I land up with a total of how much energy comes out when I make this. This is energy out when I make a bond. And therefore I can say I released 840. I put in, so let's say, you can talk about it as money. I got 1,840 out of the deal. I invested 1,370 into the deal, so I've made a profit of 430 kilojoules per mole. That is my net energy released. Let's try another example. Remember, I add energy in, and when I make the product, energy is released. Let's look at these. First thing is this revolting molecule C4H10. At this stage of your life, I would need to draw this out for you as I have here. So it's C4, 4 C's, and 10 hydrogens around it. I drew that for you, and I will in a test to an exam. Here's oxygen, double bond O. So I work out what happens for one butane. This thing, by the way, you don't have to know it yet, but it happens to have a name of butane. I take one butane, and then I am going to say it has got 3 carbon-to-carbon bonds, and those 3 carbon-to-carbon bonds are 350 each. It has got 10 hydrogen-to-carbon bonds, and those are 415 each. So I multiply 3 by 350 plus 10 by 415, and I get what one butane is worth. One butane is 5,300, but I don't have one butane. I have 2 butanes, so I multiply by 2. Don't forget about the oxygens. Oxygen is easy. It's 500, but I don't have one oxygen. I have 13 oxygens, so I multiply 500 by 13. And in total, how much money did I have to put into this? How many kilojoules did I have to put in? 16,900. That's what I went in. I then get the activated complex, which is blah, 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 lots of hydrogens, lots of carbons, lots of oxygens, and boom, out comes the product. Here's my product coming out. What's in the product? Carbon dioxide, CO2, so I need to break a CO double bond O, C double bond O. There are 2 of them in there. They're each 799, so 2 times 799. That is 1,598. But I don't have 1 carbon dioxide. I have 8 carbon dioxide, so I multiply 1,598 by 8. Then I say, what about water? Breaking OH, breaking OH. It's breaking 2 OH bonds, 460 each, 920. But I don't have 921 water. I have 10 waters, so I times by 10. And I find that if I go 8 times 1,598 plus 10 times 920, I have made a total income or total energy out is 21,984. So what's my profit? I take what I got out, I subtract what I got in, what I put in, and I am going to land up with 5,084 kilojoules per mole out at the end. So that's like a profit.